The digital thread that I'll be presenting today integrates model-based systems engineering, MBSE, with digital mission engineering, DME tools, focusing on a defense and space launch use case. This digital thread is built in Ansys ModelCenter and integrates Ansys STK and Microsoft Excel. For those who are not familiar with these tools, you can think of the digital thread as an orchestra. Each engineering tool represents a different instrument: STK for mission modeling, and Excel for automation and data analysis. Model Center, in this case, acts as the conductor, ensuring that each tool performs in symphony. When combined, these tools create a single, unified performance, a true digital twin of the mission that evolves in real time as design decisions change. Now jumping into more details, the digital thread focuses on two objectives. The first one is to model a system of systems that quantifies radar tracking of a Canadian maritime space launch. And the second is to demonstrate digital thread automation by running full cycle trait studies. Here I'll be varying radar configurations, launch trajectories, and ship paths to find the most effective setup that meets mission requirements. The mission being modeled is tracking a low Earth orbit LEO launch insertion from Spaceport, Nova Scotia. The goal is to assess how various vehicle trajectories and radar configurations affect tracking and detection metrics. There are three mission requirements that constrain the scenario. The first one is a line of sight access. All active radar combinations must track the launch vehicle for at least 300 seconds. The second one is the total costs of the mission, including fixed and operational, must stay under $300 million. And the last one is regarding the probability of detection. The combined radar network must maintain a probability of detection above 50% for at least 120 seconds. Now opening up the STK scenario and looking at the STK objects and data providers that are being integrated into the digital thread. The launch from Nova Scotia is modeled as a launch vehicle object using a simple ascent propagator defined by burnout, latitude, longitude, altitude, and velocity. To ensure realistic radar tracking, the vehicle's radar cross-section is set to 20 dBSM, or roughly 100 meters squared. There are 4 radar facilities that can be toggled on or off: 2 long-range radar sites, 1 local launch radar, and 1 mobile marine radar. Each facility includes a 1-degree field of view gimbaled sensor that is fixed on the launch vehicle with an attached monostatic search and track radar operating in the L band, 1.3 gigahertz, with a 2 Hz pulse repetition frequency, integrating 5 pulses with a probability of false alarm of 10 to the minus 6. The marine radar is mounted on a ship following a set of waypoints along the Maritime coast at a constant speed. To quantify radar network performance, a coverage figure of merit was defined to restrict access when the probability of detection exceeded 50%. In the visual overlay, most valid detections occurred near the launch site, where the signal strength was favorable for the local radars, and near the peak of the insertion, where the line of sight geometry is more ideal for the long-range, powerful radars. Switching over to Model Center, in this workflow, Excel configuration files serve as the input database for STK. These define ship waypoint, launch vehicle trajectory parameters, and radar configuration variables. By varying these inputs, we can automatically test how different mission configurations affect radar performance. The STK scenario outputs several datasets. This includes access logs for each radar facility, ship distance and speed over time, and figure of merit instances where the detection probability exceeds 50%. From there, two secondary Excel models are used. The first one is the radar performance model, which quantifies tracking quality using the figure of merit results and access times. And the second is a mission cost model, which estimates the fixed, operational, and transient mission costs. Using Model Center's design of experiments, DOE capability, the workflow can automatically run dozens of STK scenarios with different input combinations. For this demonstration, I simplified the study to focus on eastward trajectories from north to south, using both high and low LEO altitudes. The ship's path remained constant, a southbound route at low speed, while the radar configuration was set to max power and varied between local, long range, and all radars combined. This produced 30 total runs and was much more manageable compared to the over 400 possible combinations. The outputs tracked the three mission requirements outlined previously. Here I have the data organized into three tables showing different radar configurations tested at maximum power. Table 1 on the left shows the results when all radars were active. Table 2 in the middle shows only the long-range radars. Table 3 on the right only shows the local radars. Each row is a different launch trajectory, and the three columns represent the mission requirements that we defined earlier. A C means that the requirement was compliant, and the cells highlighted in green represent the valid configurations, the one that met all three mission requirements. Looking at the results, this breakdown makes sense. When all radars are active, we get excellent coverage, but all runs fail due to the cost requirement. This is because there are too many active, fully powered radars. With the long-range radars, you see valid configurations only for the northern trajectory launches. And this makes sense, as due to the curvature of the Earth, the radars will lose their line of sight tracking of the launch vehicle at lower altitudes. Finally, the local radars are compliant for all nearby LEO launches, but they struggle with high altitude trajectories due to their limited power and range. The takeaway is that each radar setup has its strengths and weaknesses. All radars maximize performance, but exceed cost requirements. Local radars are cost-effective, but range limited. And long-range radars are cost-effective, but are limited to higher latitude trajectories. This demonstrates exactly why running a trade study in Model Center is valuable. It quickly shows us not just what works, but why it works based on mission dynamics and system constraints. Ultimately, this kind of workflow shows how MBSE and DME combine to accelerate decision making, reduce iteration cycles, and ensure design traceability, all critical elements in modern aerospace mission design.